Good afternoon. Is my voice audible?
Yes, sir.
Okay. So, shall we start?
There's still a few more to come.
Okay. Let's wait. Okay, so we were discussing the Bohr's model of atom, right? So in that model, we have discussed the various points regarding the Bohr's model. We have to now see that how this Bohr's model, it explains the spectrum of hydrogen, how we get the various spectral lines when we actually observe the spectra of this hydrogen. We have seen that we get various lines, emission lines, which we call as just the Lyman series, which lies in the UV region. Similarly, the Balmer series, which lies in the visible region. Similarly, Paschen bracket Fund and Humphrey series, they lie in the IR region. So how it is possible in hydrogen there is only one electron, then how we get these many spectral lines in the spectra of hydrogen? So this was explained by the Neil Bohr with the help of this model, that is the Bohr's model of atom. So let us see how actually he explains. So let me share the screen. Is this screen visible? Raghu, is this screen visible? Can you hear me?
Yes, sir.
Okay, so let's see how this Bohr model, it explains the spectrum of hydrogen. So let's see the spectrum of hydrogen. This is explained by from the Bohr's model, spectrum of hydrogen from Bohr's model. So according to Bohr, he told that there are different shells or the energy levels, which I hope you all remember. That's your K shell, L shell, isn't it? Now see here, for example, let's say this is my nucleus here, and then let's say this is the first K shell. Let's say this is the second one, and let's say this is the third one. Similarly, let's say this is your fourth shell energy level, and then this is the next energy level. This is the next one. So now we know that when electron actually absorbs the energy, we know that when electron, it absorbs the energy, then what happens? I have told you that it gets excited. It actually jumps from lower energy level to the higher energy level, isn't it? So for example, let's say we are here having an electron in this K shell or the K energy level. So let's say this is your K, then it is your L, M. Let's say this is your N, then it is your O energy level, then it is the P, and then it is the Q. Now tell me that when actually light falls on this electron, I have already told that it will jump. It can go anywhere. So it can go into L, it can also go into this M, isn't it? So it depends upon the energy, how much energy we are giving to this electron. It can jump into any higher energy level. Now what will happen? When electron moves in the higher energy levels, it is unstable there. I have told that in higher energy levels, energy is very high. So the electron will be unstable in these higher energy levels. So what will this electron do now? It will come back. So there are various possibilities. For example, if electron is in the Q, it can jump back to this K. It can also come to this L. It can jump into this N. It can also jump into this O. So there are various possibilities. So that is why we get actually different spectral lines when we see this hydrogen in the spectroscope. When we take the spectra of this, we get the different lines. So let's see how. For example, if electron is present, let's say if electron is present in this Q and it is coming back, let's say this is the electron in the Q and it comes back to this K, that is the ground state. It comes back to this ground state, right? Then let's say we are having the electron in the P and it also comes back to this ground state. It jumps to this K, right? Similarly, if some electron is present, let's say in this O energy level, it can also come back to this K. And then similarly, let's say electron in N, it can also come back to this K. Let's say if we're having M, so it can also come to this K. And similarly, if there is electron in this L, it can also come back to this K. So these lines which we get when electron jumps from higher energy levels into this K shell, it is observed in the UV region. So that actually is our Lyman series. So this is our Lyman series. So that means in case of Lyman series, if you remember that, what was N1? Do you know that this Lyman series, it lies in the UV region? I have already told this, right? When we studied the spectra of hydrogen. So here in case of Lyman series, N1 is equal to 1. N1 is equal to 1. Now what is the N2 here? So N2, it can be, as I told that, okay, let's see here. This K, for this K, N value is 1, right? For K, N value is 1. And similarly for L, N value is 2. For M, N value is 3. Similarly for N, N value is 4. Then it's 5 here, then 6. And then for Q, N value will be 7. This is the shell number simply, or you can say as orbit number. So for this Lyman series, N1 is 1. That is this one, K. K is your N1. And now N2. N2, it can have any value that is greater than 1. That is 2, 3, 4, 5, etc. Isn't it? As you have seen here, that electron, it was actually here, let's say in this Q. For Q, N is equal to 7. So this is your 7. So it can jump directly into this K. So at that time, you get the emission line in the spectra, which lies in the UV region. So that is actually your Lyman series. So I hope that these here blue lines, they actually are your Lyman series. They are the emission lines which we observe in the UV region, ultraviolet region. Now let's see the second one. Second was your Balmer series, which actually lies in the visible region, right? Do you remember this Balmer series? So in this Balmer series, I have told that it lies in the visible region. So when we will get this Balmer series, when actually electron, it is in the higher energy level, and when it comes back to this L shell, right? Let's say this is the electron which here comes into this L. This was the key, and this is your L here. Similarly, let's say we are having electron here, and it also comes into this L. And let's say we were having electron in this O, so it also comes back to this L. Similarly, let's say electron was in this N, it also comes to this. And let's say electron was in M and it comes to this, L. So that means at that time, we will get the spectra which will lie in the visible region. So we call these lines as Balmer series. So it is simply a series of lines, emission lines, which we actually observe in the spectra of hydrogen. So that means Balmer series, it is observed when N1 is your 2, because all the electrons which were in the higher energy levels, they are just coming back to this L. They are not coming back to the K, the ground state, but they are just jumping from higher energy levels. Electron is jumping from higher energy levels to this L. So that means here N2 can be 3, 4, 5, 6, 7, etc. Got it? So in case of Lyman series, I told that according to the Bohr's model, Neil Bohr told that there are various orbits are the energy levels, which we call as K, L, M, N, O, P, Q, etc. And for these energy levels, N value is already given by the Bohr. He told that N is 1, that is the first orbit. Similarly, N is 2, That is your second. And when electron is in the higher energy level and it comes back to the K, at that time we get the Lyman series. So this is how Niels Bohr explained the spectra of hydrogen. And similarly, when electron, it is in the higher energy level and it comes back to this L, not the K, it comes back to this L. At that time, you get the Balmer series. So I hope that you have understood now this. Now you can easily explain the third one. What was the third series? Can you tell me the name of the third series? It was the Paschen series, right?
Yes, sir.
Exactly. So in this Paschen series, I told that it lies in the IR region, that is the infrared region, IR region. So when we will get this one? We will get this when electron in the higher energy levels, it will come back to the M shell, isn't it? So that means what will be here N value? N value will be 3, as I have already told it. And N2 here will be 4, 5, 6, 7. It can have anything value, but it should be greater than N1. N1 is 3, so N2 will be 4, 5, 6, 7, 8. Are you getting? Yeah, so this is the Paschen. Exactly. So have you noted down this? Shall I move to the next page?
Yes, sir.
So that means, let's say, for example, if you are having, let's say this is the nucleus. Let's say this was your the first orbit key, and let's say this is your L. This is your M. Let's say this is your N. Let's say O. Then let's say this is your P. This is your Q. Let's say this is your R1. So now can you tell me here that if I told that in the Paschen series, electron which is in the higher energy levels, it will just jump. Let's say this is the electron, this black dotted. It will jump to which one? So the first was your key, and then it's your second L. It will just jump to this M shell. So electron will jump into this M. So at that time, we get the Paschen series. So similarly, if electron is in this higher energy level and it comes back to this M, so at that time, you will also get the Paschen series. That means we will get those emission lines which actually lie in the IR region, infrared region. So this is your Paschen series. What was the next one? Fourth one? That is the bracket series,
Sir,
right?
bracket series.
Exactly, bracket series. So in this bracket series, we know that what was the it lies also in the IR region, right? IR region, infrared region. And I told that for this N1 is your 4 and N2 will be,
5, 6, 7.
it will be 5, 6, 7 extra. Exactly. So that means here in this case, if electron is, let's say here in this higher energy level, which I am showing this blue dot, so it will just come back to this N. It will just come back to this N energy level, or you can see the N orbit. So at that time, when electron from the higher energy levels, it jumps into this N orbit, we get the bracket series. So this will be your bracket series here, bracket series. And similarly, now tell me if we are having, what was the next one? Next was one fund series, right? Yeah, it's the fund series. P remains silent. So it also lies in the infrared region. You can see the for infrared region, right? For infrared region. For IR region. For infrared region. So here what you will observe, that, let's say this is the electron in the higher energy level. So it will just jump into which? It will jump into this O. It will jump into this O. So similarly, the electron in this energy level, it will also jump into this O. So here you will get the fund series. So for this N1, what will be the N1 value? So you remember that for this key N1 is 1, isn't it? For this L, N1 is 2, and then it is 3, 4, 5, 6. So that means here N1 is 5, right?
Yes, sir.
And N2, it will be your 6, 7, 8, etc. Okay, what was the last one? Last series was the Humphrey series. So in this Humphrey series, it lies very far infrared region, very far IR region, very far infrared region, right?
Yes,
So I
sir.
had told you that for this Humphrey series, N1 is equal to 6 and N2 will be equal to 7, 8, 9. So this one I can show with this, let's say the yellow dot here. So that means electron will jump into this N6. So these two yellow lines which I have shown, so they are your Humphrey. They will be observed in the very far infrared region. So that is your Humphrey series. So have you got that how this Bohr's model explains the spectra of hydrogen?
Yes, sir.
Yes, exactly. So now this is very important. I hope that you have noted down this. Shall I move to the next page?
Sir.
Shall I move to the next page?
Sir, yes, sir.
Okay, so now here you have to remember that how many emission lines you will get. There is a formula to calculate the number of emission lines. Number of emission lines. This formula is very important for competitive exams like NEET. So how many emission lines you will actually observe in the spectra of any element? So that is given by number of emission lines. It is given by the formula which you have to remember. So that is just like this. That is N2 minus N1, then into again N2 minus N1, then it is plus 1 upon 2. This is the formula with which you can calculate how many emission lines you will actually observe in the spectra of hydrogen. So divide it by 2. For example, question is asked like this. For example, how many emission lines you will observe? How many? Emission line is actually observed when electron jumps from higher energy level to the lower energy level. So how many emission lines are observed? When an electron jumps from fifth orbit to, let's say, to the second orbit. So if electron jumps from fifth to the second orbit, so can you tell me how many emission lines we will observe here? So what is the formula? Simply N2 minus N1. So first of all, tell me what is here N1, what is here N2, given in the question. Can you tell me? N1 is always having smaller values. So this second, that is your 2, it is your N1, and the higher value, that is your fifth orbit. So that is N2 is equal to 5. Got it?
Yes, sir.
Okay, so tell me now, what is the formula? N2 minus N1. So N2 is your 5 minus 2. And then again, it is that is again here 5 minus 2 plus 1. So you will divide it by 2. So what is the answer coming?
Sir, I got 6.
Exactly, it will be 6. So there will be 6 emission lines which we will observe in the spectra when electron jumps from fifth orbit to the second orbit. Is it now clear? Any doubt here, anybody?
Yes, sir.
Okay. So then I hope you will remember this formula, then you can easily calculate the number of emission lines. So that means it is now very easy that when you actually take the spectra, when it is given that when electron jumps from, let's say, fifth to the second orbit or any orbit to any orbit, you can calculate the number of emission lines. It becomes easy with this formula, so you have to remember this. Okay, then let's move ahead. Shall I move to the next page?
Yes, sir.
Okay. So next we have to see here. Energy we have already seen. I hope you remember the three formulas in order to calculate the energy, isn't it? Let's see now what are the limitations of this Bohr's model of atom. What are the limitations? Limitation number first is that this Bohr's model actually explains the spectra of hydrogen, but it actually explains the main lines of spectra. But in the spectra, when we actually use the sophisticated microscope, we actually observe that there are some fine lines also, very small lines are also observed in the spectra. How these small lines are actually obtained there, Bohr couldn't explain. So that's why you will write that the first limitation of Bohr's model is that, and that this Bohr's model could explain main lines of spectra but could not explain fine lines of spectra. Bohr's model could explain Bohr's model could explain main lines of spectra but could not explain fine lines of spectra. That means there are also some fine lines are observed. Fine lines of spectra. But could not explain fine lines of spectra. Second limitation is that this Bohr's model is actually applicable only for the hydrogen atom. Hydrogen and hydrogen-like species. It is not applicable for multi-electron atoms. So I will write it like this, that this model is only applicable for hydrogen and hydrogen-like species, for hydrogen atom and hydrogen-like species. And hydrogen-like species. What are hydrogen-like species? That means those species which actually contain only one electron, just as I have in the questions I have told that He positive. Similarly, Li2 positive. All these have only one electron. Similarly, Be, beryllium 3 positive. All these have only one electron, so they are hydrogen-like species. So for these, you can apply the Bohr's model, but it is not applicable for multi-electron atoms. But this model is not applicable. This model is not applicable for multi-electron atoms. So whenever there are multi-electron atoms, we cannot apply this Bohr's model to that multi-electron atoms. So multi-electron, we can have just helium onwards. That means up to the last element, that is the oganesson. So that means this Bohr's model, it is only limited to the hydrogen and hydrogen-like species, but we cannot apply this model for multi-electron atoms. That is simply, you can see that this Bohr's model, it could explain the spectra of hydrogen, but it could not explain the spectra of multi-electron atoms. So multi-electron atoms, they actually constitute our helium, lithium, beryllium up to the oganesson. Got this point?
Yes, sir.
Third limitation is that this Bohr's model could not explain Zeeman and Stark effect. So there are two important effects. One is known as Zeeman effect, and another is known as Stark effect. Could not explain Zeeman effect and Stark effect. Now, what is this Zeeman effect? It is actually the splitting of spectral lines when we actually give magnetic field. When atom is placed in the magnetic field. Similarly, Stark effect means the splitting of spectral lines in presence of electric field. Okay, let me explain on the next page. Have you noted down this? Shall I move to the next page? Have you noted down this?
Yes, sir.
Okay, so what I told, what is Zeeman effect? Can you define this? What is Zeeman effect? It is simply, you will write, it is the splitting of spectral lines spectral lines in presence of magnetic field. For example, okay, let me explain. For example, if this was the spectral line which we actually observe in the spectra of hydrogen, but now if you are just giving magnetic field here, let's say this is the north pole of the magnet and this is the south pole of the magnet, place it here. Then what has been observed that this spectral line, it actually splits into two lines. So why this actually happens, this could not be explained by the Niels Bohr. So this is the limitation. So he could not explain why this Zeeman effect takes place, why this splitting of spectral line takes place. Similarly, the another is what? Another is the Stark effect. So what is Stark effect? It is also the splitting of spectral line, but in presence of electric field, right? So I will write it here. It is the splitting of spectral lines, in presence of electric field. So if we just give the electric field, then also what happens? The splitting takes place. So why this splitting takes place? Bohr could not explain. So for example, if we are having, let's say this is the hydrogen atom, let's say we get this one spectral line in its spectra. And now here what we are doing, we are just giving the electric field. And I hope you remember that how to give the electric field. We are just taking the two metal plates. We are connecting one with the positive terminal of the battery and another metal plate, it is connected to the negative terminal of the battery. So at that time, it is observed that this spectral line, it gets splitted into two lines. So why this splitting takes place? He could not explain. So I hope you will remember this, what is the Zeeman effect and the Stark effect. Shall I move to the next page?
Yes, sir.
Okay. So what is the next limitation? Next limitation is that he could not explain. Actually, see, this Bohr's model, it is actually planar. It is a 2D model, but actually when we see the atom, it is 3D. It is having three-dimensional structure shape. So we can write that he could not explain the 3D structure of atom. So he could not explain 3D structure of atom, three-dimensional structure of atom, right? Okay, next limitation is that's he didn't actually told regarding the shapes of molecules. For example, different molecules have different shape. Why these atoms combine? So what is actually happening there? So nothing Bohr could explain regarding this. So that means you will write that he could not explain shapes of molecules. That how we are having different shapes in different molecules. Next very important limitation is that he could not explain the two very important experimental observations that is known as de Broglie's dual nature of matter. We will study this ahead. So the next topic will be the de Broglie's dual behavior. So he could not explain de Broglie's dual nature of matter. And another experiment which was later done, that is known as Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. So these are two very important topics which we will study now ahead. So first you remember here that limitation is the limitation of Bohr's model is that he could not explain de Broglie's dual nature of matter and Heisenberg's uncertainty principle. These are very two important topics regarding the examination point of view. So Heisenberg's uncertainty principle. So these were the limitations of Bohr's model. So actually these two which I told here, one is the de Broglie's dual nature. They are very two important observations which were actually seen after the Bohr's model. So it is the talk of actually 1926, 1927. So let us see first of all, what is this de Broglie's dual nature of matter? So have you noted down this? Shall I move to the next page? Have you noted down this? Shall I move to the next page?
Yes, sir.
Okay. So next topic which we had studied, that is the which we have studied in the last limitation, that is the de Broglie's dual nature. De Broglie's. So de Broglie is the name of scientist. De Broglie's dual nature of matter. So now we know that according to Einstein, he told that any electromagnetic radiation, light has dual nature, isn't it? According to Einstein, what he told that light has dual nature. It has both particle as well as wave nature. So now, so we know that light has dual nature, isn't it? That means some phenomena can be explained by taking the particle nature of light, and some phenomena can be explained only when we take the wave nature of light. So now what he actually de Broglie told here. According to de Broglie, he told that any material object, any microscopic particle can also have dual nature. So it was the de Broglie. It is the talk of 1924. De Broglie. So de Broglie in 1924, what he told? He told that every microscopic particle, so that means we can have various microscopic particles like electron, like proton, isn't it? Electron, we are having proton, we are having neutron, we are having atoms, we are having molecules, we are having, all these are microscopic particles, isn't it? So every microscopic particle has dual nature. According to de Broglie, he told that every, like the light has dual nature. He told that every microscopic particle, electron, proton, neutron, atoms, molecules, they also have dual nature. That means both particle as well as wave nature. Both particle as well as wave nature. Both particle as well as wave nature. Got it?
Sir.
Okay. So then de Broglie, he gave an equation known as de Broglie's wave equation. So he gave an equation known as de Broglie's wave equation. De Broglie's wave equation. Yes, are you having any doubt? So what is that de Broglie's wave equation? Okay, de Broglie's wave equation is that lambda is equal to, lambda is the wavelength, it is equal to h upon mv. H is the Planck's constant, you already know this. M is the mass of electron, and mass of any material particle, any microscopic particle, and v is the velocity of that particle. So I will write here that m, it stands for mass of particle. That's actually the microscopic particle. That can be your electron, that can be your proton, that can be your neutron, and v is the velocity of particle. So actually what he told that every microscopic particle in motion, actually it should be in motion, right? Every microscopic particle in motion, because when particle is in motion, then it can have the wave nature. If it is at rest, then it could not have, then the velocity will be zero, but it should be in motion. When it is in motion, so that means it will have some velocity, right? Okay, so you will remember that according to de Broglie, he told that every microscopic particle which is in motion, it has dual nature. It has both particle as well as wave nature. So whether it is your electron, whether it is your proton, whether it is your neutron, whether atom, whether molecule, whenever they are in motion, they will have wave nature. That means this de Broglie wave equation, you have to remember here, he gave the equation known as de Broglie's wave equation, which is lambda is equal to h upon mv. Now, can anybody tell me what is this mass into velocity known as? Mass into velocity. This is what? This is known as linear momentum, isn't it? I had told this. It is known as momentum, correct?
Yes, sir.
So that means you can also write lambda is equal to h upon p. Can you write like this? That is lambda is equal to h upon p. Isn't? Yeah, we can write because the mass into velocity. So have you noted down this? Shall I move to the next page?
Yes, sir.
Now, the next thing is that we will see how to derive this de Broglie's wave equation. This is very important. This is asked in the exam, that how to derive this derivation. So derivation of de Broglie's wave equation. So how we can derive this? We can derive this from two very important principles, from two equations. That is actually Einstein's equation and the Planck's quantum equation. So can you tell me what is the Einstein's equation? Einstein's equation. Can anybody tell me what is Einstein's equation? That is E is equal to
equals mc square.
exactly mc square. Okay, let's call this as equation first. And then can you tell me the Planck's quantum equation? What we call as Planck's quantum theory? What is the equation? Planck's quantum equation. That is E is equal to h nu, isn't it? We have studied the Planck's quantum theory.
Sir.
We know that E is equal to h nu, right?
Yes, sir.
Okay, now can you combine these two? What we will get? So can I write like this? That is I can write that h nu, it is equal to mc square. Can I write like this from these two equations? Yes, I can write like this. We know that E is equal to mc square and E is equal to h nu, so I can write h nu is equal to mc square. Now we know that this nu is the frequency. So how is this frequency calculated? Frequency is always equal to c by lambda, right? C by lambda, wavelength. So that is equal to mc square. Got it?
Yes, sir.
Yes, one C and one C will get cancelled here. What we will get? We'll get H 1 by lambda, or you can simply say H by lambda. It will be equal to MC, correct? Now, can
Yes,
I
sir.
write it like, okay, so I can also write it like this. So this is my H by lambda, so it is equal to MC. So MC has nothing in the denominator, so I can write like this, 1. So H into 1, so that's your H, or you can say just like this, lambda into MC, so that's equal to lambda MC. So it will be equal to H. So what will be lambda? Lambda is the wavelength, so it will be equal to H upon MC. Got it?
Yes, sir.
Yes. Now what he did here, what was the C? C was the speed of light, right? So in place of C, now he told that we will take V. V is the velocity of any material object. So that means we can write lambda is equal to H upon mv, mass into velocity. Mass into velocity. So this is the de Broglie's wave equation. You have to remember that here, actually m, it was the mass of the photon, and c was the speed of photon. But here he replaced it. He told that just like any electromagnetic radiation, like any light, any electromagnetic radiation has dual nature. De Broglie told that any material microscopic particle which is in motion, it will also have dual nature. It will also behave like a wave. So you have to remember this wave equation, de Broglie's wave equation, and how to derive this. This is very simple. It is derived from Einstein's equation and Planck's quantum theory, Planck's quantum equation. That is E is equal to mc square and E is equal to h nu. So you will get here lambda is equal to h upon mv, or you can simply also call it as lambda is equal to h upon p. P is the momentum, right? And we know that momentum is equal to mass into velocity. Got it?
Sir.
Shall I move to the next page?
Yes, sir.
Okay. So now we know that this lambda, it is the wavelength, it's equal to h upon mv. Now another equation is derived here. We know that kinetic energy. Can you tell me kinetic energy, how it is calculated? It is always equal to 1/2 of mv square, right? 1/2 of mv square, isn't it? Kinetic energy is always equal to 1/2 mv square. Now if I just multiply this equation by 2m, so can I write like this, that multiply whole equation by 2m. So how can I write it? I will write that 2 into m into kinetic energy. So it will be equal to 1/2 of mv square into 2m. Correct? Can I write it like this? Yes, we can, because we know that 2m and 2m, it will get cancelled, and we will again get kinetic energy is equal to 1/2 of mv square, isn't it? Now tell me here that 2 and 2, it will cancel. M into m, that is m square. So I will write it like this, that is m square into v square. So it is equal to 2m kinetic energy. 2m kinetic energy. Now can I write it like this? That is m square v square, it is equal to 2m kinetic energy. And then I can also write it like this, and that is mv is equal to mass into velocity, it will be equal to, it is here square, when it goes on this right side, it will become root, so under root of square root of 2m kinetic energy, isn't it? Now substitute this value in this equation. So we know that lambda is equal to h upon mv. So what you can write in place of mv? You can write root of square root of 2m kinetic energy. So this is another equation which you have to remember. So these two equations are very important, equation first and equation second. So have you noted down this? Any doubt here, any confusion? Is it clear?
It's clear, sir.
Okay. So now next what you have to remember, that this de Broglie's wave equation is actually only significant for microscopic particles. It is not too much significant for macroscopic particles. So you will write it here that de Broglie's dual nature, de Broglie's dual nature is significant only for microscopic particles. That means which are very, very small, right? They will actually have the wave nature. The big particles do not have any wave nature. So can you guess that, for example, if we are having any vehicle, if we are having any ball, cricket ball, and that cricket ball is in motion, and let's say any vehicle, it is in motion, it is moving on the road. Have you seen that this car, it is having some wave nature, it is just moving like the waves? No, not at all. So that means this wave dual nature, that is the wave nature associated with any material particle, it is only observed when particles are very small, when they are microscopic, like we are having electron, proton, neutron. So that means this de Broglie's dual nature, it is significant only for microscopic particles, not for macroscopic, not for macroscopic, not for macroscopic. Macroscopic means which are very big. It is macro, and it is macro, right? That was the microscopic. So have you got it? So you have to remember that this de Broglie's dual nature, it has significance, it has importance only for microscopic particles. It is not having significance for macroscopic. Macroscopic means which are very big particles, which are having bigger size. I will explain it by solving a question on the next page. So can you tell me, have you noted down this?
Yes, sir.
Okay. So let's see here that why it is only significant for microscopic particles only. So let's say we are having an electron. Let's say it is moving with the speed of, let's say the speed of electron is, let's say it is 2 into 10 to the power 6 meter per second. Let's say this is the speed of electron, correct? Let's say this is the speed of electron. So electron is moving with a velocity of 2 into 10 to the power 6 meter per second. So can you now calculate the wavelength for this electron? What will be the wavelength according to the de Broglie's wave equation? So lambda is equal to h upon mv, right? Now we know that h is the Planck's constant. Yes, it is 6.626 into 10 to the power minus 34 joule second, right? and we have to divide it by mass into velocity. So what is the mass of electron? Can you repeat it? 9.11 into 10 to the power minus 31 kg, right? And what is the velocity? Velocity, I told that it is 2 into 10 to the power 6 meter per second, isn't it? But important is here unit conversion. So can you tell me what you can write in place of this joule? Do you know what is 1 joule? How much is the value of 1 joule? This is very important. So first of all, tell me that if you are having work. So can you tell me work in physics? Work is always equal to force into displacement, isn't it? Force into displacement, correct?
Sir.
Okay, now can you tell me what is the force? Force is mass into acceleration, right? Force is always equal to mass into acceleration. Now tell me the unit. Now what is the unit of work? Work unit, it is joule. Work unit, the unit of work is, SI unit of work is joule, right? So 1 joule is equal to mass, it is mass, it is unit is kg, SI unit. Now acceleration, it is what is the unit of acceleration? It's meter per second square, right?
Sir.
Okay, what is this? S is the displacement, so it will be meter. So that means you can write that 1 joule is equal to 1 kg. Now tell me meter into meter, what will be that? That will be meter square per second square. Got it?
Yes, sir.
Okay, now tell me what I can write in place of this joule. So in place of this joule, you can write kg meter square per second square, isn't it?
Yes, sir.
For this, yeah, exactly. Okay, now, can you tell me in place of this joule second, what I can write in place of this joule second? For example, if I will write joule second, so joule second means it is your kg meter square per second square. Now 1 second. So in place of joule second, you can write like this, that is kg meter square per second square, and then it is your second raised power 1. So it is second raised power minus 2, second raised power plus 1. So what it will become? It will become kg meter square per second. Got it? Second inverse. So this you can write in place of joule second. So I will now simply write in place of joule second, what I can write? I can write like this. I can write here that it is my kg meter square, and then it is second inverse. So now tell me what will get cancelled. Can you cancel the units? Kg and kg, it will cancel. Meter and 1 meter from here, it will cancel. Per second and per second, it will cancel. So what you got here? You got only the meter. And you should get the meter because we had to calculate the wavelength. So wavelength, it will always come in the unit meter. Correct? Got it? Okay, so can you now solve this one? So it is now 6.626 divided by, so it is 9.11 into 2. So what is that? That is 18.22, right? Now tell me, it is here 10 to the power minus 34. Now here it is 10 to the power minus 31. When it will just come up, it will become 10 to the power plus 31. Here it is 10 to the power 6. When it will just come up, it will become 10 to the power minus 6, isn't it? So can you solve this now? So for example, it is my here 2 9s are here. And similarly, you can write 2 3s are. So 3 1s are, 3 3s are 9. So it is 1 by 3. Approximate, you can just take it as approximate. You have not calculate the actual value. So into, can you solve this one? When base R sum power should be added. So minus 34 and plus 31. So that is 10 raised to power minus 3, and minus 3 and minus 6. So that is your 10 raised to power minus 9 meter. Got it?
Sir.
Is it clear? Okay. Now 1 by 3. So that is how much? 0.33, isn't it? Into 10 to the power minus 9 meter. Or you can approximately write it like this. That is 3.3 into 10 to the power minus 10. Can I write like this? 3.3 into 10 to the power minus 10 meters. So this is the wavelength of an electron which moves with a velocity of 2 into 10 to the power 6 meter per second. Got it? Now, note down this value. This is very important because we will then compare it with any big particle, that is the macroscopic particle. So this is the wavelength of a microscopic particle, that is 3.3 into 10 to the power minus 10 meter. Actually, this is a big value which you can easily observe and which you can easily calculate, and which is actually lying in the electromagnetic spectrum. This value is lying there. But when now we will see the macroscopic, that is the bigger one particle. So shall I move to the next page?
Yes, sir.
Okay, now let's have another question. Let's say we are having a cricket ball. So what will be the mass of cricket ball? How much is nearly the mass of a cricket ball? Can you tell me? And let's say it is 0.6 kg. Let's take the mass of a cricket ball as 0.6 kg. And let's say it is moving with the same velocity, that is 2 into 10 to the power 6 meter per second, isn't it? Are you getting? Can you then calculate the wavelength here? What will be the wavelength of this cricket ball? So we know that lambda is equal to h upon mv, mass into velocity. Now we know that h is the Planck's constant, that is 6.626 into 10 to the power minus 34 joule second. Now in place of joule second, I have already told that I can write kg meter square per second. In place of joule second, I can write kg meter square per second. Okay. Now tell me, what is the mass? Mass I have told as 0.6 kg. So can I write 0.6 as 6 into 10 to the power minus 1 kg? Isn't it? I can write like this. Is it right? Have you got it? Can I write 0.6 as 6 into 10 to the power minus 1 kg? Yes, I can write. I have told this. It is the simply conversion. It is just converting this 0.6 into this scientific number, and that is 10 to the power. Okay, what is the velocity here? It is the same, that is 2 into 10 to the power 6 meter per second. So first of all, what you will do, you will just cancel out the units. If units are getting properly cancelled, that means your question is going right. So kg and kg it will cancel. 1 meter and 1 meter will cancel here. Per second and per second will cancel. So you will get meter. So that is the correct, because wavelength, it should be in meters. So now tell me here, okay, let's take the approximate answer here. So you can just take it as 6. So 6, it is just 6 ones are 6. Okay, 1 by 2. You can take the approximate value 1 by 2 into, now it is 10 to the power minus 34. Then it was here 10 to the power minus 1. When it will just come up, it will become 10 to the power plus 1. It was 10 to the power 6. It will become 10 to the power minus 6. It is in meters. So 1 by 2, that is 0.5 into 10 to the power. Now tell me, it is 10 to the power minus 34. And it is 10 to the power plus 1. So it will be 10 to the power minus 33. And minus 33 and minus 6. So that is minus 39. Got it? So that is, you can just take this approximate as 5 into 10 to the power minus 40. Got it? Have you got it? This is the approximate answer which you will get here.
Yes, sir.
Okay, now this is very important. Have you noted down this wavelength? How much is this? Is it a very big value or a very small value? Can you tell me, is this a big value or a very small value? It is 5 into 10 to the power minus 40.
Yes,
Is
sir.
it a bigger value or a smaller value? Why don't you respond?
Sir, can you repeat it again?
I'm just saying that this wavelength, that is 5 into 10 to the power minus 40. Is this number, is this wavelength bigger or very small value?
Sir, sir, I think it's the same size.
It is very small. See, it is 5, then you have to divide it by, it is 10 to the power minus 40. So that means you have to divide it by 4. You have to divide it by 4, and then how many? Okay, sorry. You have to divide it by 1, and then how many zeros? 40 zeros, isn't it? So what will be the value coming here? Can you tell me what will be the value? Value will be very, very small. It will be 0.0000 up to large number of zeros we are getting here. So this wavelength is very small, which is neglected. It cannot be calculated. It is not easily observable. It doesn't lie in the electromagnetic spectrum. So that is why I told that this de Broglie's dual behavior, it is not actually applicable for macroscopic particles. It is only applicable for microscopic. Have you got it now? It is only applicable for microscopic particles. Clear? Okay, I will write it here. That is why de Broglie's dual.
Sir?
Yes.
Sir, I forgot to inform you. I have another tuition, so I have to leave at 6:30.
Okay, you can leave, no problem. You can leave at 6:30.
Thank you, sir.
Most welcome. So that is why de Broglie's dual nature is not significant. It is not having any importance for macroscopic, that is MAC, for macroscopic particles. It is only significant for microscopic, which are very small. Just we are having the electron, we are having the proton, we are having the neutron. For these, it is significant, but it is not having any significance for macroscopic particles. That means which are very big particles. So got it here? Have you noted down this? Okay. So let's move.
Yes, sir. You can move to the next slide.
Sure. Now, what we had to see here, we have to now see that what is the actually experimental evidence for this dual nature. But first of all, you will just remember that we know that lambda is equal to h upon mv, or you can just call it as lambda is equal to h upon p. Now, what is lambda? It is the wavelength, right? Lambda is the wavelength, isn't it? So that means I can write it is inversely proportional to the momentum, correct? It is inversely proportional to the momentum. So higher the momentum, less will be the wavelength, lesser will be the wavelength, correct? Or you can simply say that wave nature, it is inversely proportional to the particle nature, because actually momentum, it is the property of a particle. So you can write that wave nature, it is inversely proportional to the particle nature. So more the particle nature, less will be the wave nature. So if particle nature is very high, that means if any particle is having higher mass, so then its wave nature will be very less. So it is one of the same thing, whether you call it as momentum or the particle nature. So if any particle is having very high momentum, then its wave nature, wavelength, it will be very small. Just as we have seen in case of cricket ball, the wavelength came very small. That was 5 into 10 to the power minus 40. So that is very, very small, which is negligible. Got it? So now let's see the experimental evidence of experimental verification of first we will see the experimental verification of particle nature of electron. So electron has particle nature, we already know this, but let us give the experimental verification how it was actually experimentally seen. So when actually we bombard these electrons, let's say this is a beam of electrons. When it is actually bombarded on zinc sulfide screen, so can you tell me what will happen? If this is my zinc sulfide screen and these electrons, they strike this zinc sulfide screen, what will happen? It will just glow. I have already told that when electrons strikes the zinc sulfide screen, it will start glowing, isn't it?
Sir.
Exactly. And what is that known as? So it glows and produces a bright spot, right? What is that bright spot known as? Can anybody tell me what is that bright spot known as? So you'll remember that this bright spot, it is known as scintillation. K/ES, it means known as, so it is known as scintillation. So this is what we actually observe here, that when electrons strikes the zinc sulfide screen, you have to remember that it starts glowing. It produces a bright spot known as scintillation. Now, you have to remember that when one electron strikes, it produces one bright spot. So this bright spot, it is localized. It is at its own position. So that means this electron, which is producing this bright spot, it will have particle nature because particles are always localized. Okay, have you noted down this? Shall I move to the next page? Then I will explain what is the difference between particle and a wave.
Yes, sir.
Okay. Okay, let me first see this. Okay, let's see here that what is the difference between a particle and a wave? Can anybody tell me what is the difference between particle and a wave? Particle, it is always localized, isn't it? Particle is localized. Localized means it remains where it is. It is having a fixed position in the space, right? But this wave, it is always delocalized, isn't it? Wave is delocalized. It doesn't remain only at a one place, at a one point. Delocalized. Wave is always delocalized. Correct? Have you got it?
Sir.
Okay, now what I told that, for example, if I'm having this one electron and this just strikes the zinc sulfide screen, then it produces only one bright spot. So only one, let's say this is here, the bright spot here. Only one bright spot is produced. And this bright spot, I told that this is known as scintillation. And I also told that this bright spot, it is localized. It is only at a one point. So what does it indicate? It indicates that it is having particle nature because particles are always localized. So the electron which is producing this bright spot on this zinc sulfide screen, so that is also having the particle nature. So this is how to observe the particle nature of electron. Then we have to see the experimental verification of wave nature of electron. So let's see the experimental verification of wave nature. I'll move to the next page. Let me write it here, experimental verification of verification of experimental verification of wave nature of electron. So electrons have also the wave nature, which is actually told by the de Broglie. So let's see its experimental evidence. So the experimental evidence, it was actually, the experiment was done by Thomson and Davison and Germer's experiment. Okay, I will write it here. Davison and Germer's experiment. So what they did, Thomson and Germer, they just have a crystal of nickel. So let's say this is a crystal of nickel here. This is a, let's say, crystal of nickel. And what they did, they just bombarded the electrons on this. So when electron was bombarded on this crystal of nickel, so it is just a beam of electrons. So then the zinc sulfide screen was just put here. Okay, I will just now show it like this. That on the zinc sulfide screen, what they observed on a photographic film, they observed that they get a diffraction pattern. A diffraction pattern was observed here, like this. I will show it here. Let's say this is my zinc sulfide screen. So when these electrons, they actually, what they here, they will just scatter here. Diffraction will actually take place here. And this diffraction was actually observed here on this zinc sulfide screen. And it was observed that we get a diffraction pattern, that is dark concentric circular rings. So these rings were obtained on photographic film. So what does this ring indicate? These dark concentric rings, what they indicate? Can you tell me? These dark concentric circular rings, they indicate that these electrons, they are actually having the wave nature. This is very important that you have to remember this, that when beam of electron, it is actually bombarded on a crystal of nickel by Davison and Germer, what they observed, they just observed that a diffraction pattern is obtained here. It is the talk of 1928. So they observed that we get a diffraction pattern, which actually consists of, these are just your dark concentric rings, circular rings, dark concentric circular rings known as diffraction rings. It is just simply a diffraction pattern, diffraction. So it indicates that these electrons have wave nature because the same diffraction pattern is observed when we just have X-rays. When X-rays are actually bombarded on a crystal of nickel, we get the same diffraction pattern. Since X-rays, we know that they are the electromagnetic radiations, they have the wave nature. So these electrons which are producing here the same dark concentric circular rings as produced by the X-rays, so they will also have the wave nature. So it indicates that they have wave nature. So it indicates that they have wave nature. So electrons have wave nature. It was experimentally observed by Davison and Germer in 1928. Similarly, 1927, there was another scientist whose name is Thomson, also have the same experiment, but he just took the crystal of gold. He didn't took the crystal of nickel, he took the crystal of gold. And what he observed the same pattern. He got the same diffraction rings, which clearly indicate that these electrons are having wave nature also. So this was the experimental verification that when beam of electron, it is just bombarded on the crystal of nickel, we get the dark concentric circular rings. These rings indicate that they have the wave nature, because these concentric circular rings, they are delocalized. And I have told that waves are delocalized, isn't it? These are delocalized. That means they are not only at a fixed position, they just separate like the waves. We know that waves separate, isn't it? This is just a wave. So wave is not localized. I told that wave is delocalized. So that means you have to remember that this electron, when it is bombarded on the crystal of nickel, we get the diffraction rings. Diffraction takes place here, and these diffraction rings, they are delocalized, they are not localized. So it indicates that they have the wave nature. So have you got it now? Is it clear?
Yes, sir.
So have you noted down this?
Yes, sir.
Okay. So let's actually then revise what we have studied today. So we have just started from the Bohr's model, that how Bohr's model actually explains the hydrogen spectrum. I told that according to Bohr's model, there are various energy levels, what we called as shells. We are having K, L, M, N, O, P, Q, etc. When actually electron absorbs the energy, it goes into the higher shells. It goes into the higher energy levels. But electron is unstable there. So what it will do, it will just come back. When electron comes back from excited state, from the higher energy level to the lower energy level, so it will emit radiation. And that is actually observed in the spectroscope. That means we get the various spectral lines. So if the spectral line is observed in the UV region, that is your Lyman series, because actually electron is coming from the higher energy levels, it comes back to the ground state, that is the key. For K, n value is 1. And similarly, when n1 is 2, that is your Balmer series, that lies in the visible region. We get the Balmer series. The various lines are observed when electron jumps from higher energy levels and it comes to the L shell, or we can say the L energy level. And similarly, next was the Paschen series. I told that when n1 is equal to 3, then it is your Paschen series. It lies in the IR region. That means the electron is coming from the higher energy levels and it is just coming back to the M shell. And similarly, when electron in the higher energy level, it comes to the N shell. So that means at that time we will get the next series. What is the next series? That is the bracket series. Similarly, when n1 is equal to 5, that is your Pfund series. And when n1 is equal to 6, that is your Humphrey series, isn't it? So here you have to remember the n1 and n2 values in various series, what we actually observe in the spectra of hydrogen. And you have to remember that in which spectral region they actually lie. So Lyman series, it lies in the UV region. Balmer series, it lies in the visible region. Then we are having the other series, they lie in the infrared region. Just Humphrey series, it lies in the very far infrared region. Got it? Okay, then I just told that what are the various limitations of this Bohr's model. I told that he could not explain the spectra of multi-electron atoms. He could not explain the fine lines of spectra. Then I told that this Bohr's model could not explain the Zeeman effect and the Stark effect. Similarly, I told that there is limitation that he could not explain the shapes of molecules. Also, you can remember the shapes of molecules. And he could not explain the Zeeman and the Stark effect. And similarly, the two very important experimental observations, they are just your de Broglie's dual nature and the Heisenberg's uncertainty principle. Then we just move towards the de Broglie's dual nature. I told that according to de Broglie, he told that every microscopic particle which is in motion, it will have dual nature. It will have both particle as well as wave nature. Then I told that he gave an equation known as de Broglie's wave equation, that is lambda is equal to h upon mv, or you can say h upon p. Then I told that how to derive this. It is derived from the two very important equations, that is Einstein's equation, E is equal to mc square and E is equal to h nu, that is the Planck's quantum equation. Then I told that this de Broglie's wave equation, it is only significant for microscopic particles, not for the macroscopic ones, not for the bigger particles. Because when actually you apply this wave equation for the bigger particles, the wavelength comes out to be very small, which is negligible, which is not easily observable, which cannot be easily measured. So then I just told that what is the experimental verification of this particle and the wave nature. I told that particle nature, it is simply explained when electron, it is just bombarded on the zinc sulfide screen. What we get a bright spot known as scintillation. So scintillation, bright spot, it is localized, it is only at a one point. So that means it indicates the particle nature. Then I told that when these electrons, they are just bombarded on a crystal of nickel, that is the experiment done by the Davison and the Germer, and simultaneously another experiment was done by the Thomson by taking the crystal of gold. What they observed that when beam of electrons, it falls on crystal of nickel or the gold, we get the diffraction pattern, that is the dark concentric rings. So these rings are delocalized, they are not localized, so that indicates they have wave nature. Correct? Okay, any doubt, any question in today's lecture?
No, sir.
Anybody? Chitesh? We're having Ananya? Yeah. Any doubt
No
here?
doubt, sir.
Okay. Chitesh, are you having any doubt? Shivita?
No doubt, sir.
Okay. So let's stop then today's class here. Have a nice day ahead. Wish you all the very best.
Thank you, sir.
Most welcome.